So we have seen the remark that if A and B are countable sets, then their union, A union B, is also countable. So let us see the theorem. And the statement of the theorem is that if A1, A2, A2 and so on are countable sets, then their union of A n varies from 1 to infinity is also countable. That means, in words, a countable union, the countable union of countable sets is countable. Okay, so let's prove. So it is the easy way to prove. So we consider sets as A1 is with 11, A1, A2, A3 and so on, A2 with. So to identify this element of the sets, I'll use the elements again. I will repeat the elements, and to identify whether they are elements from the set A1 or A2, I will mention here. So these are elements from first set A1, these are elements from second set A2, and similarly An can be identified with elements A1, A2, A3 from the set An, right? So suppose A1, A2 are all countable sets. What we wish to show? Their union is countable. So A K with J written at the superscript, it means it is the kth element of set AJ. Okay. So we suppose that A1, A2 are all countable sets. So let us define the height of AKJ to be J plus K. So A11 is only element of height 2. A1 and A2 are only elements of height 1 plus 2 or 2 plus 1 equal to 3. Similarly, A13, A22 and A31 are only elements of height 4, right? And so on. So we can have the order of the elements, the list of elements in the increasing order of their height will be, the list will be by this way. And so on. And care should be taken that, note that we should remove the element AK that has already counted, that has been already counted. It is simply it means we count the elements of union of A n by the order. Which order? Suppose I list the element of A1 as this, elements of A2, A1, A2, A3, by this way, elements of A3 and so on. So, and elements of A4 by this way. So, I should count by this way. A11, element of height 1 is, height 2 is the only element, then element of height 3, these two elements A12 and A21, then elements of height 4 are this A31, A22, then A13, right? Then element of height 5 this way, and it will go here. Right? So this is the list, a list of elements in their increasing order of the height. So the fact that this counting scheme counts every element, so the this counting scheme counts every element, right, from any AI. So if we can count the elements, so we can have, it can be equivalent to set of integers or a set of positive integers, right? So union AN is equivalent to set of positive integers. Therefore, union AN is countable. Okay. So the next thing is the corollary. The set of all rational numbers is countable. So we prove. So the set of rational numbers can be written as union of En. So what is the union? So we shall define En to be set of rational numbers which can be written in this form: 0 by n, 1 by n, minus 1 by n, 1 by n, minus 2 by n, 2 by n, and so on. That means 0 positive rationals with denominator n and negative rationals with denominator n. So each En will be then equivalent to z, because in this way we can also assign a counting scheme, because the difference is what? This is the set En with denominator n and numerators are nothing but integers. So each En is equivalent to z, set of integers, and we know that z is countable and z is countable. Therefore each En is countable. And as each En is countable, so countable union of countable set is countable. We have seen the theorem. Therefore, union of En is countable, as it is countable union of countable sets. The next theorem is if B is an infinite subset of the countable set A, then B is countable. That means if A is countable and B is subset of A, then B is also countable. So proof: let A is infinite countable set with these elements and is countable suppose B is subset of A. So each element of B is some AI. That means as B is subset of A, so every element of B is some element from this set A, right? So let n1 be smallest integer or a subscript, so that an1 is element from B. Similarly, let n2 be next smallest integer or subscript, so that an2 is also in B. So then what will happen? Continuing by this way until all the elements of B are exhausted. So then the set B will have this much element an1, A and 2. So that is the elements of B are labeled with N1, N2, N3 in this way, and similarly labeled with 1, 2, 3 and so on. So it is equivalent to set of positive integer. Therefore, B is countable. Now, for example, S is set of all rational numbers in 0, 1. All rational numbers in 0, 1, then S is countable. Since Q is the set of rational numbers is countable, and as S is set of all rationals in 0, 1, so S is definitely a subset of Q. Therefore, by above theorem, S is countable. That means infinite subset of countable set is countable. So let us see some assignment to you. What is the date? The date is 16 December. So the first assignment. Show that the intervals open interval 0, 1 and closed interval 0, 1 are equivalent. That means you have to define a one-to-one correspondence or a function which will be a one-one function between these two intervals. Second thing, show that n cross n, that means the Cartesian product of integers, is a countable set. It is nothing serious. We know the set of natural numbers, the set of positive integers is countable. So you have to collect their order pairs n cross n. So you can have the order pairs 1, 1, then 1, 2, 1, 3, 1, 5 and so on in the first row. In the second row you will have 2, 1, 2, 2. So here also you have to collect the element with some height. So there is only one element with the height 1 plus 1 equal to 2. Right? Then what are the elements of height 3? 1, 2 and 2, 1. The elements with height 4, 3, 1, 1, 3 and 2, 2. By this way. So we can assign a counting scheme. So then n cross n will be countable. Next thing, show if A and B are countable, then the Cartesian product A cross B is countable. And next thing, we have seen that set of integers is countable. So if A is countable set and f from A to B is onto, then B is countable. Okay, so and one more thing is there. If A and B are countable, then A intersection B is also countable. Next thing, the set 0, plus or minus 1 by n varies from is countable. Okay. Please add some more problems here. Next, any open interval A comma B is equivalent to any other open interval C comma D. The next one is the intervals close bracket 0, 1 and semi open bracket are equivalent. Also close bracket 0, 1 and semi closed 0, 1 are also equivalent. And the next thing, any interval is equivalent to the set of R of real numbers. So try to find the map which can give a one-to-one correspondence between the two intervals.